All right, so this is part 5 of Unit 2, and we are going to start looking at rational functions. Now, a rational function is just a polynomial over another polynomial. And anytime we have variables in the denominator, we always want to make sure that our denominator does not equal 0. So the first thing we're going to look at with rational functions, leading kind of from there, is that we want to look at what the domain of the function is. Again, making sure that we are restricting the domain so that we are not including values that would make our denominator 0. Now, looking at this first example here, and hopefully we can see this clearly enough. Yep. We have a polynomial where our denominator is already factored, so that's nice. And looking at those values on the bottom, we can tell that x cannot equal 0 because of that lone x there, 2, and -5. Well, that tells me what x cannot equal, but that doesn't state what the domain is. And I think it's really helpful to think of a visual here. If we think of a number line, we have -5, 0, and 2. We know x cannot equal any of those values. So I'm going to go ahead and put open dots there. But x can equal anything else. Every other x value is just fine. So the rest of the number line is shaded. So if I were to state my domain, it's all the shaded area. Well, that would be -infinity to -5. We're not including -5 because it can't equal -5. And then this interval would be -5 to 0, and then 0 to 2, and 2 to infinity. So that would be the domain. We have 4 different kind of intervals here, so we have to list it with 4 different intervals here. The next example, we need to go ahead and factor our denominator first. And if I factor that, I have x over x plus 3 and x minus 3. So that means x cannot equal positive or -3. So again, kind of thinking about that number line, if you wanted to draw a number line, again, it's not asking us to, but it's got a helpful visual. It's going to be everything except for those values. So my domain then would be -infinity to -3, -3 to 3, and 3 to infinity. The next example, if you notice this denominator, it cannot be factored. I could try, it's not a difference of squares, it's a sum of squares. So there's no formula for us to factor that. If I tried using the x method or anything like that, there's nothing that I could do to figure out what would that would factor to. I'd have to use imaginary numbers. So what that means then is that there's no restriction. There's no x value that would make my denominator 0. Let's just say you thought there was a value. We plugged in, let's say, 0. Well, 0 plus 9 is still 9. That's not 0. If I plugged in 3, 3 squared would be 9. 9 plus 9 is 18, not 0. If I plug in -3, -3 squared is 9. 9 plus 9 is 18, again, not 0. There's no values that make the denominator 0. So that means my domain then is -infinity to +infinity. There are no restrictions on it. The next thing we're going to look at with rational functions is our most basic rational function, and that's the function 1 over x. And when we are working with this function, if I wanted to plug in a bunch of values just to first kind of discover what the function looks like, then we can kind of go ahead and do that. So I'm going to plug in these values, plugging in -100, that would be -1 over 100. If I plugged in -10, that would be -1 over 10. Plugging in -2, that would be -1/2. Plugging in -1, that would be -1. Plugging in -0.5 or -1/2, that would be -2. Plugging in -0.1 would give me -10. Plugging in -0.01 would give me -100. But plugging in 0 we can't do because 1 divided by 0, well, our denominator can't equal 0. So this is undefined. Now, similarly, for the positive values, it's all these same numbers, but positive. So 100, 10, 2, 1, 1/2, 1/10, 1 over 100. Now, when we have this undefined value here, what this does is it creates a vertical asymptote. Anywhere that would make your denominator 0 is going to give you a vertical asymptote. The equation of this vertical asymptote is the equation x equals 0. So that's the equation of the vertical asymptote. Now let's go ahead and plot these values. So I'm not going to plot the 100 because obviously this graph is too small for that, but I'm going to plug in most of the values. So if I plugged in, let's just start with negative 0.1. So negative 0.1, that's just barely past 0, but it would give me all the way down to negative 10. And then if I plugged in negative 1/2, so negative 1/2, that would give me negative 2. If I plugged in negative 1, I would get negative 1. If I plugged in negative 2, I would get negative 1/2. If I plugged in negative 10, I'd get negative 1/10. That's going to get really small. If I plugged in negative 100, if I plugged in all these other values and got further and further, closer, there's nothing negative enough, negative 1,000, negative 10,000, negative 1,000,000, that will make me actually touch the x-axis. It's going to get infinitely close but never actually touch. So the shape of this graph is this kind of really tight curve in here. It gets really, really close to the y-axis here, but it can't actually touch because that would make our denominator 0. So we'll see here on this side, and we're going to see it again on this side, that we're going to have a horizontal asymptote. It's going to get really, really, really close to something, but never actually touch it. And again, we have these similar values on this side. So plugging in 0.1, we get 10. Plugging in 1/2, we get 2. Plugging in 1, we get 1. Plugging in 2, we get 1/2. Plugging in 10, we get 1/10. So we get this, again, really tight curve in here. And I'm not drawing it perfectly. I'm kind of touching the x and y axis a bit on that side. But you can see here that there's no number big enough that I can actually touch the x-axis. I could plug in 1,000, 1,000,000, 10 million, whatever, and it's going to get really, really close to the x-axis, but never actually touch it. So we have a horizontal asymptote, the equation y equals 0. Okay. So that's kind of how rational functions behave. They have these vertical and horizontal asymptotes. We're going to see that they can also have what are called slant asymptotes and these things called holes. So we'll look at that a little bit closer in just a minute here, but this is the most basic rational function that we could have. Okay. So flipping the page, one of the next most basic rational functions that we can have would be the equation 1 over x squared. It's kind of hard to tell here. There we go, 1 over x squared. Before we get into that, actually, I'll come back to this here after we have a graph to kind of use as an example. So we'll come back to this in just a minute. So, again, 1 over x squared. Let me zoom in a tad here. We're not going to make a big table like we just did for 1 over x. We're going to just kind of leave it, not do quite as much background work for it. But we can plug in some values. We can think about what it would be. And if I make a table and I have x and f of x, and let's just say I plug in, let's just plug in from negative 2, negative 1, let's do negative 1/2, or negative 0.5, however you want to think about it, 0, positive 1/2, positive 1, and 2. Now if I plug in negative 2, well, negative 2 squared is 4. That's going to give me 1/4. If I plug in negative 1 squared is 1. 1 divided by 1 is still 1. If I plug in negative 1/2, negative 1/2 squared would be 1/4. 1 divided by 1/4 is 4. Plugging in 0, we would be dividing by 0 again. So again, that one is undefined. And plugging in 1/2, we're going to have similar values. 1/2 squared is 1/4. 1 divided by 1/4 is 4. 1 squared is 1. 1 divided by 1 is 1. Plugging in 2, 2 squared is 4. So that would be 1/4. So notice that none of these values are negative. The fact that they're squared means that they're both positive. So we can go ahead and plot these values. At negative 2, we had 1/4. So negative 2, 1/4. Negative 1 was 1. Negative 1/2 was 4. 1, 2, 3, 4. And it's going to take on that same shape that we just saw in the previous example. And again, we can't plug in 0 because that would make it undefined. So we have that same shape, and you'll see that shape a lot with rational functions. And we can see that we're starting to have these vertical and horizontal asymptotes again. Plugging in positive 1/2, we have 4. So positive 1/2, we have 4. Positive 1, we have 1. Positive 2, we have 1/4. And again, I can connect those and draw that graph. So we can see that, again, we have a vertical asymptote here at the y-axis. That's the line x equals 0. And I have a horizontal asymptote here at the x-axis. That's the equation of y equals 0. So that's my horizontal asymptote. I'll usually abbreviate that as HA, and my vertical asymptote as a VA. Now we're going to go back to this notation that we kind of looked at up here briefly, and then I said I'd come back to. This is describing what's what's happening as x is approaching a certain value, either from the right or from the left. So if you see a notation that looks like this, what this means is as x gets closer to a from the right-hand side. That little plus sign means from the right side. So if I was looking at as x, let's say as x is getting closer to 0 from the right-hand side, so as my x values are getting closer to 0 from the right, my function is getting closer to infinity. So f of x is going to infinity. So we can describe where something is doing a certain behavior. Okay. Now we can also say, okay, well, what if we're approaching x from the left-hand side? So as x is approaching 0 from the left-hand side, that's what that negative sign means. Approaching from the left-hand side, f of x is also going to infinity. Okay. Now, the next symbols we see here as x goes to infinity and x goes to negative infinity, well, we can also talk about as x goes to infinity, gets larger and larger and larger, f of x, in this case, is getting closer and closer to 0. And similarly, as x goes to negative infinity, my function is getting closer and closer and closer to 0. Okay, so that's what those notations mean. In calculus, after this class, you'll eventually talk about the concept of limits. This notation, as well as kind of what we're talking about here, is one of those main first topics in calculus. So you'll see that more in calculus, but you'll get a little introduction here. Now the first thing we're going to do here is look at how to find our vertical asymptotes. So if you have a rational function and we find where the denominator equals 0, those will give us our vertical asymptotes. However, if any roots cancel with the numerator, meaning if we have a factor on the top and bottom that cancel out, those are called wholes rather than vertical asymptotes. And we'll see graphically how those are different. So as first example here, we have x over x squared minus 1. And we can go ahead and factor that. X plus 1, x minus 1. And none of those factors cancel with the numerator. So what that means then is that I have vertical asymptotes at x equals negative 1 and x equals 1. And you do want to write them like this, x equals negative 1 and x equals 1, not just the numbers, because these are actually equations. Notice the vertical asymptote here is an actual line. So we need to have an actual equation for these vertical asymptotes. Now, because of this glare here, it's kind of hard to see the equations. Let's see if I can zoom in a tad more and make it better. All right, so with this next example here, we have x minus 1 over x squared minus 1. So again, factoring that denominator, x plus 1 and x minus 1. And then on top we have x minus 1. We see that these cancel out here. So that means we have a whole at x equals 1. And then we have a vertical asymptote at x equals negative 1. So this is still a vertical asymptote, but at x equals 1, since those would cancel out, we would have a whole. Now the next example, Again, a similar example to one we saw earlier where it is not possible to factor that denominator. There are no values that would make it equal to 0, which means that this has no vertical asymptotes. Okay. All right, let's go ahead and move on to the next page here. And now we're going to look at horizontal asymptotes. Now, horizontal asymptotes are a little bit more involved in finding what the horizontal asymptote is. So there's going to be 3 different cases that we will look at here. This is what we're looking at here right now is this part of your notes. Again, if we have a polynomial over another polynomial, and these are my largest terms here, then what I'm looking at is the degree n and the degree m of the top and bottom. And we're also going to look at their leading coefficients. So first, if the degree n of the top is less than the degree of the bottom. So in this case, we're saying if the degree of the top is less than the bottom. So the bottom is bigger. So you can just kind of make a note here, bottom. This is the case where the bottom degree is bigger. Then the equation y equals 0, which is the x-axis, is your horizontal asymptote. Now, if the degree of the top and bottom are equal, then what you'll be using is the equation of y equals their leading coefficient of the top over the leading coefficient of the bottom. So equal is going to be your horizontal asymptote. Okay. And then if the degree of the top is bigger, then there's no horizontal asymptote. So top bigger. Okay, so if the top is bigger, then there's no horizontal asymptote at all. Okay, so let's do some examples here. So let's find the horizontal asymptote if there are any. In this first example, the degree of the bottom is 2, the degree of the top is 1. So in this case, the degree of the bottom is bigger. That means our horizontal asymptote is the equation of y equals 0, which is the x-axis. Okay. Now the next one, the degree of the top and bottom are the same. They're both x squared is their largest exponent. So that means their leading coefficients are going to give me my horizontal asymptote. So my horizontal asymptote is y equals 4 over 2, which is y equals 2. Okay. And the last one, the degree of the top is bigger, x cubed over x squared. So that means there's no horizontal asymptote. Now there is one more possibility here. There's actually this thing called slant asymptotes. You don't see them very often because there's only a specific case where they could occur. And that is if the degree of the numerator is exactly 1 more than the degree of the denominator. So for example, if you have y equals and you have x cubed over x squared, blah, 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 something like that, where the degree of the top is just exactly 1 more than the degree of the bottom. And then you would use long division or synthetic division to find what the slant asymptote is. You would divide, go ahead and do this divided by this, and your answer then would be your quotient. So y equals the quotient is what your slant asymptote is. Again, we don't see these very often, but it is possible to have a slant asymptote. Okay. All right, so when we are graphing rational functions, if we can do it with transformations, meaning shifting up, down, left, and right, kind of like we saw with the whole HK thing earlier in the course, then we can do that. If not, then we will use some other tools that we'll see here in just a second. So here I have a long list of tools that can help us with graphing rational functions. And when we're graphing rational functions, we can determine if it has even or odd symmetry. We can use y-intercepts, x-intercepts, vertical asymptotes, holes, horizontal asymptotes, slant asymptotes as well. We can plot points in each interval, and then we can just kind of use all of those things and plug in points to piece together our graph. So we're going to do several examples of these. Our first example here is one where we can just use shifting. So we already graphed 1 over x squared earlier in this video. And what we're going to do is we're going to use that graph and knowing what that looks like, and we're going to shift it. Well, inside the graph, this minus 2 means we're going to move to the right 2. And then this plus 1 means we're moving up 1. So before, when we graphed this function here, we had horizontal asymptotes at the x-axis and the y-axis. But that y-axis one is going to move to the right 2. And the x-axis one is going to move up 1. So that gives me my new asymptotes here. And I can still plug in some points. I'll just use f of x here, actually, not y, to plot what my graph looks like exactly. So if I have a vertical asymptote, you want to choose a few points to the right of it and a few points to the left of it. So I'm going to plug in 1 and 0. And then a couple points to the right would be 3 and 4. And I'm plugging those into this equation here. So if you plug in 0, 0 minus 2 is 2, 2 squared is 4, 1/4 plus 1 would be 1 and 1/4, which is 5/4, which is about, or is exactly 1.25. Plugging in 1, 1 minus 2 is -1, -1 squared is 1, 1 divided by 1 is 1, plus 1 is 2. Plugging in 3, 3 minus 2 is 1, 1 squared is 1, 1 divided by 1 is 1, 1 plus 1 is 2. Plugging in 4 is going to be similar to plugging in 0. Again, it'll be 1.25. So we can go ahead and plot those points. At 1, we had 2. And at 3, we also had 2. And at 0, we had 1.25, so just above that asymptote there and just above the asymptote here. And we know the behavior of these graphs. We know the shape of them. So there we go. And that's our graph. So shifting it is kind of nice because it's not a whole lot of extra work. It's just shifting a graph we already know how to graph. This next example is not one where we can use shifting. It's 2x minus 1 on top and then x minus 1 on bottom. And we can use whatever tools we have at our disposal. So the first thing I always try to find are the asymptotes. So in this case, finding my vertical asymptote is whatever would make my denominator 0, and that would be 1. So my vertical asymptote is x equals 1. My horizontal asymptote, we need to look at the degree of the top and bottom. Well, they both have degree 1 on top and bottom, so that would be their leading coefficients, and that would be y equals 2 over 1, which is 2. So once I have those asymptotes at x equals 1 and at y equals 2, 1, 2, we can see what our asymptotes at least look like. Now, from here, if you have one vertical and one horizontal, there aren't many options. You're either going to have that shape of the curve here and here, here and here, or in opposite diagonal corners here. So what we're going to do here, and I actually just put a mark on there, is we're going to go ahead and try to plug in some points. Again, we know the shape of the graph, so we don't have to plug in a lot. We can just plug in a few points on each side. So if my vertical asymptote is at 1, I'm going to plug in 0 and -1. And then I'm going to plug in 2 and 3. And plugging into the function here, if I plug in 0, well, that's 0 and that's 0. -1 over -1 is just 1. If I plug in -1, -1 times 2 is -2. -2 minus 1 is -3. Plugging in -1, -1 minus 1 is -2, so that's 3 over 2. And then plugging in 2, 2 times 2 is 4. 4 minus 1 is 3. And then 2 minus 1 is 1, so 3 over 1 is just 3. Plugging in 3, 2 times 3 is 6, minus 1 is 5. And then 3 minus 1 is 2, so 5 over 2. So that gives us some points to plot. So we have 0, 1. and -1 3/2, so that's 1.5. And that kind of lets me see my shape of graph here. And this is the amount of detail I'd expect on a quiz or an exam, of how much detail I'd want to see. Plugging in 2, we have 3, so up 1, 2, 3. And then 2.5, 5/2. We can see the shape of that graph, and that's it. A couple more examples, and then we'll wrap up this video here. We have 2 more rational functions here that we're going to graph. And number 3 here, we have 3x squared over x squared minus 4. It's helpful to factor the denominator if it's possible. So I can go ahead and rewrite this as 3x squared over x plus 2 and x minus 2. From there, we want to go ahead and find our asymptotes again. So vertical asymptotes are what make our denominator equal 0. No factors cancel, so there's no wholes, but that will be x equals 2 and x equals -2 as our vertical asymptotes. So it is possible to have more than one vertical asymptote. You can only have one horizontal asymptote. You can't have more than that. You don't have to have a horizontal asymptote, but you can't have more than one. We have the degree on the top and bottom is the same, so those leading coefficients there, y equals 3/1, which is 3, is our horizontal asymptote. So let's go ahead and plot those. Horizontal asymptote at 3. And vertical asymptotes at 2 and -2. From there, again, I can plug in a few points. Okay. And we're going to plug in some points in between the 2 vertical asymptotes and then on each side. So let me make that a little bit bigger here. -1, 0, and 1 will give us in the middle here. And then I'm going to plug in a couple points over here. Oh, -1, -2, so -3 and -4. And then I'll do 3 and 4 on the side. Okay. All right, and just for the sake of time, plugging these in, I'm going to go ahead and tell you what they are. When I plug in -1, I get -1 to my function. Plugging in 0, I get 0. And then plugging in +1, I also get -1. So I can go ahead and plot those points. Again, you can plug them in and just evaluate those. I just didn't talk through plugging them all in here. But we're going to get this almost parabola-like shape here. That's the middle. Plugging in -3 and -4, -3 gives me 27/5. Again, -3 squared is 9, 9 times 3 is 27. Plugging in -3, -3 plus 2 is -1, -3 minus 2 is is -5, -1 times -5, so 27/5. Plugging in 4, we have 48/12, which is 4. 27/5 is 5.4. And then plugging in 3, 27/5 as well, and 48/12, which is 4. So plotting those points, at -3, we had 5.4, so 1, 2, 3, 4, 5.4 is almost 5.5. And then at -4, we had 4. So again, we're seeing the shape of that graph. And then we have the same points over here and the same shape of graph. So you can see that we have all 3 of these areas covered here. You'll have something on this side, something in between your asymptotes, and something on this side. Now, when we have our graph divided up into 3 different kind of columns here, where we'll have something here, and something here, it's possible that you have these 2 here. It's possible that they could both be down here, or it's possible that they could be on opposite diagonals. The middle part really only has 3 options as well. It could be a parabola going down, a parabola going up, or it could be like a kind of a cubic shape like that. Okay, not a lot of possibilities. All right, Last example here, we have x to the fourth over x squared plus 1. And because the degree of the top is bigger, there are no horizontal asymptotes. There's nothing, if I tried to factor the bottom, there's nothing within real numbers that would factor that, and so there's nothing that would make the denominator 0, so there's no vertical asymptotes. In order for us to have a slant asymptote, there would have to be the degree being just one more on top than bottom, but it's two more, so there's no slant asymptote. And there's no factors between the top and bottom that cancel, so there's no holes. So that gives me no information. That doesn't give me any clues about what this is going to look like. What we can do if that happens is we could think about dividing this. If the degree of the top is bigger, then I could use synthetic division or long division. And if I divide a degree 2 polynomial into a degree 4, what I'd be left with is something degree 2. I would have my quotient of that division would be a quadratic, meaning it would have a parabola shape. So what I can do then is I can just start with plugging in some values now that I have the understanding that this is going to have a parabola shape here. So I can plug in, let's just start with -2, -1, 0, 1, and 2. Let's just start there, and if we need to plug in more values, we can. If I plug in -2 to this function, -2 to the fourth power is 16, and then -2 squared is 4, plus 1 is 5. So that is 3.2. Okay. Plugging in -1. -1 to the fourth power is 1. -1 squared is 1, plus 1 is 2, so 1/2. Plugging in 0, 0 divided by 0 plus 1 is 1, 0 divided by 1 is 0. And plugging in 1 and 2 is going to give me the same values here, 1/2 and 16 over 5. So I can go ahead and plot those values. 0, 1 gave me 1/2, -1 also gave me 1/2. 2 gave me 3.2123, a little bit above that. And same thing on the other side. And now we have this parabola shape, and that is my graph. So we've done a few different examples of rational functions, but the reality is there's no way to cover every possibility. So you might see something that looks different than these 4 examples. It might change a little bit, so be prepared and practice graphing various rational functions. We'll pick up in the next video with part 6.